SNPs with larger customer values for the extension mechanism. We can see that the DS score has the same problem as in the hexaple data by keeping a constant utility value and not converging to one with larger privacy budgets. To summarize, our project focuses on privacy-preserving selection of top-end relevant SNPs. Our creative point is to add Laplace noise directly to the count of constituency table, which reduces the amount of noise added to the final classifier statistic values. I have learned how to select top-end most relevant SNPs and the differential privacy, and how to adapt the privacy-preserving frequent pattern mining techniques in our context. In the future, we plan to develop more advanced privacy-preserving algorithms to select top and most relevant SNP combinations. We already have a paper submitted to 2014 Translational Biomedical Conference. Finally, I will send to my mentor, all the collaborators, all professors, staff, and all the other interns, the iDASH, BBMI, and NIH. So much for my presentation. I will be happy to answer any questions you have.
So we have 2 minutes for questions. If you want to ask a question, you may ask that you repeat on the microphone.
Yes, so the top SNPs are selected for the entire set of sample or selected for each individual?
It's selected for the entire set of samples. Yeah.
So at the end of the project, what do you actually release? Seems like you focus on perturbing the cell frequency table of table, but so you are not releasing too much allele for individual level, you release only a count too much people. Is that what you release?
Repeat the question.
Yeah. Do you release allele frequency individual level, or do you release only the summary 2x2 table for each state?
Here we don't release the 2x2 contingency table or the allele table. Here we just select the index of the top 5 SNPs among all the SNPs. And to perturb the allele contingency table, we just want to compute the noisy classifier statistic values and then select the index of SNPs according to these noisy classifier values. So it's just a middle process.
Thank you. Thank you for your presentation. The next presentation by Ken Chang, Precise Privacy Preserving Biologists, Quality Implement Service. He is a PhD candidate in electronic computer engineering from the University of Oklahoma, Tulsa. He had bachelor's and master's degrees from China University of Geosciences and Beijing University. And his mentors from Oklahoma. Thank you.
Hello everyone. Today I'm going to present the proposed precise framework, which is short for privacy preserving cloud assisted quality improvement service SCAP. My project member is Dr. Shang. My name is Go Chen. I'm a PhD candidate from University of Oklahoma. This is joint work with Dr. Norman Muhammad and Dr. Xiaotian Zhang. Here is the outline of today's presentation. Suppose a few neighboring hospitals in a county want to aggregate their local private medical data to perform some meaningful scientific discovery to improve the healthcare. However, due to the privacy concerns of institutional regulation, hospitals may not be able to exchange the data with others. Existing data dissemination methods such as differential privacy protect sensitive medical data by introducing noises on the raw data, but it is also degrade data utility. In contrast, the proposed framework tries to preserve the accuracy of results without introducing additional noises, and we resort to the combination of a silent encryption method to achieve this goal. The proposed framework is mainly based on two basic cryptographic primitives as shown in this slide. They are homomorphic encryption and double circuit. I will walk you through the detail of each primitive in the next few slides. Before introducing homomorphic encryption, let's first take a look at the traditional encryption method, where the data privacy is protected by data encryption using the storage or transfer implicit. However, for any further data analysis, one must first decrypt the data. To apply certain operation over the decrypted data, we need to apply certain operation over the decrypted data. Then, finally, one can obtain the answer. The major privacy risk in the traditional method comes from the requirement of decryption before performing any additional operation. In contrast, in the homomorphic encryption framework, one can perform certain operation directly over the encrypted data. And the decryption operation is only required when one wants to obtain the final results. Therefore, we can minimize data privacy risk during all life cycle of data processing. Despite this advantage of homomorphic encryption, it is worth mentioning that homomorphic encryption only supports limited operations such as addition or multiplication with a high complexity overhead. Now let's introduce the other cryptographic primitive, the double circuit. First, let's introduce a traditional circuit as shown in this slide, which can evaluate the function fxy by taking one input x from Alice and another input from y from Bob. However, the privacy of inputs cannot be guaranteed in this circuit due to the lack of protection. Then is counterpart the double circuit and evaluate the same function, but by taking double input with double output, where only authorized user can decrypt the double output. Therefore, we can preserve both Alice's and Bob's data privacy, as none of them input the raw data. Let's start with a traditional framework without privacy protection to illustrate the task. Suppose there are m hospitals, where each has its local private data, such as the mortality of a subpopulation. Then each hospital may want to rank the mortality among all neighboring hospitals and compare with average mortality in a cloud environment. In case without privacy protection, all hospitals need to send their raw data to the cloud. That cloud can compare the data and rank for each hospital. Finally, the cloud returns the results. Each hospital gets its mortality rank and the comparison with the average mortality among all hospitals. The hospital may make necessary adjustments to improve the health care if it has a higher mortality than that in other hospitals. However, the pre-setup requires the exchange of raw data, which will to protect data privacy. Next, we will introduce the proposed privacy-preserving framework. In the new framework, we introduce an actual remote service provider, which will cooperate with the cloud to answer the hospital's queries. First, the remote service provider sends the public key to all hospitals on the cloud for homomorphic encryption. Each hospital will use public key to encrypt data and send the encrypted data to the cloud. Because cloud does not have a private key, it learns nothing from encrypted data. Based on homomorphic addition and multiplication, the cloud can compute the encrypted average over all inputs. By then, the cloud has n+1 encrypted data. In the next step, the cloud generates n+1 random masks. The cloud encrypts all the random masks using the same public key. Then add each of them with corresponding encrypted data following homomorphic addition property. The cloud will get n+1 encrypted summation of the data and the random mask. The cloud will send this encrypted item to the remote service provider. Because the remote service provider has private key, it can decrypt all encrypted items. However, because all decrypted items contain random masks, the remote service provider cannot learn the actual data. If the random mask generated by the cloud and the decrypted items with additive mask from the remote service provider, the cloud and the remote service provider can first generate double inputs, which can be fed into double circuit for privacy-preserving comparison. The double circuit will subtract the double random mask input from the double input provided by the remote service provider in a private preserving manner. In other words, all the intermediate results in the double circuit are still double values. Then, the double circuit performs comparison operation over this double value data to get hospital ranks and their comparison with average mortality without reviewing any raw data. Finally, the cloud will send the ranks and the comparison to the corresponding hospital, and the hospital can use this information as reference to improve their SL. We extracted 924 SU record data from MIMIC 2 clinical dataset. This table shows the attributes of each record. We evenly split the SU record among 4 hospitals. This table shows the comparison result under different criteria. For example, the figure 13th, 14th, or 15th unmarried person. For each criteria, our method securely outputs the ranks of each hospital. In this table, the red ranks indicate the corresponding mortality is above average in the corresponding criteria. This slide shows average execution time of each key cryptographic operations over 1,000 tiles. We can see that the double circuit is the most time-consuming operation. Moreover, we provided the estimated execution time of the same operation that was applied on the plain text as a reference. This is a summary on the future directions. We have implemented the arithmetic and comparison operations in cryptographic method based on cloud and model. In the future, we will build advanced systems such as regression model. We will speed up the computations through parallel computing. This is the paper submission during my internship. Finally, thanks to my mentor, collaborators, and all professors, staff, interns. iDASH, EVMI, and
Question?
I want to know how many operations your system can support.
now we just implement the comparison and arithmetic operation.
Plus, minus, times.
Multiplication.
Yeah.
Multiplication is numeric equation, and the comparison operation in arithmetic.
Thank you. The next speaker is Shirley Wong for the assessment of privacy and disclosure risk method. Shirley is a third-year PhD candidate at the Department of Statistics from Yale University. His master's doctorate. He specializes in high-dimensional analysis, prevention, reduction, facial basis.
Thank you for Dr. Monomosheto's introduction. Today I'm going to talk about using the intervention method to assess privacy data disclosure risk here. My mentor is Dr. Sasaki. As introduced before, I'm a third-year PhD candidate in the Department of Statistics at Yale University. So what motivates our project here? Sometimes when we do code research, we collect the data, and usually this kind of data contains categorical variables and continuous variables. And before we release this kind of data, we would want to process the data. Like we have to remove the sensitive information or the explicit identifiers. And once the data is released, insurers, like hospitals or the insurance companies, they would want to match their client's record to a target group in this data set. And if the probability that they can match the record to this target group is high, that means this person's record can be easily identified. And that proves that this person at a really high risk. So the higher this probability is, the higher this risk is. And that is why this probability is constantly used as a matter of the risk. And therefore, we need to build up an accurate estimation of such kind of probability. So far, people have been transformed continuous variables. They either remove the variables or mean the continuous variables, like high level, medium level, or low level. And further, they place strong assumptions on distribution, like assume the distribution should follow a distribution or a Poisson distribution. But we don't want to group continuous variables because group continuous variables always lose this information. So we want to keep the data as strong as possible. And in statistics, there has been a model that estimates the probability, but that model places a strong assumption on the dependency structure between the continuous variables, between the discrete variables, and between the discrete and continuous variables. And once again, we don't want to place such kind of arbitrary assumption. And that makes our drawn probability density function a really complex one. And this is the area that has not been touched yet. So I'm not going to go into details of the folder of my model, and I'm not going to show his proofs here. But I want to point out several things here. Our model mainly consists two parts. One is a proportion estimation, another one is a probability estimation. And in this current estimation, there is a bandwidth matrix that needs to be decided so that this current density, the KDE method, is accurate. And during this internship, I proved that our estimation is asymptotically unbiased, and the variance the variance is bounded. And having this too is proved, I also show that our estimation shows more magnetic. Because we have proven that the more magnetic here, we can further build up the confidence interval later. And I've also provided a optimal solution to choose the bandwidth matrix so that this KD is more accurate. So in order to visualize, I did some simulations, and I'm going to show you some of them here. In one of the simulations, I set two boundary variables. That means the data would be divided into 4 subgroups, and within each subgroup, there are 3 continuous variables. And this variables should follow a multi-dimensional Gaussian distribution whose covariance matrix not always have non-zero elements on the open parts. So that means when we look at these points into the 3D space, we would expect to see that these points would form some kind of an ellipsoid. So the first row here has 2 pictures from the real distribution, and the second row here is our simulation. We used the estimated probability density function, and we used the Monte-Carlo method here to simulate our data. And as can be seen here, our simulation generally covered the real distribution of the 4 groups structure is preserved here. Another way to generally compare the estimation and the real data here is that despite comparing the contours here on each plane, on the XY plane, XZ plane, and YZ plane, and as you can see, the contours generally agree with each other. We calculated the ratios between our estimated probability density and the real density, and we expect to see the ratios to be around 1, because that is an indicator that our estimation is close to the real density. And as you can see here, both of the previous method and our methods show ratios that are neatly around 1 here. My method has a shorter, narrower here, so that's an indicator that our method outperforms the previous one. As mentioned before, we proved the normality, and we can therefore build up the confidence interval of the estimation. The graphic here, the blue line here is the real density, and in this confidence interval curve here, we can see that my method either completely covers the real density, or it is closer to the real density. And another way to compare the performances here is by looking at the box plots. And my method almost always covers the real density, but the previous method fails to do so in 2 meter area. So in our future work, I need to apply this theory with data that is collected from the real world, and I want to further compare the proposed bandwidth matrix that I announced in this internship with the other bandwidth proposed before. And once again, I want to thank you for assessing time, and special thanks goes to John Lee, who has helped me so much with checking my groups during this entire internship. So I'm ready to take questions.
I have a question. Your simulation is on a proposed distribution. Have you did any experiment on a real data set?
That is my
you explain rank and access? It's like
I ranked these distributions. I ranked the samples by the real density. So the bigger the real density is, the bigger the rank is. So when you look at yeah. Yeah. So by simulating like 1,000 samples and I calculated the real density and we rank the samples by the real densities.
Thank you. Thank you. And we are proceeding with the presentation of semi-online support vector machines by Jeremy. These statistic vectors in the web for computer engineering, focusing on intelligence audits, the pursuit of the data in method. There is a yes, I
Good morning, everyone. I'm Ari Ramner, and I'm going to talk about my project, my Summer Internship project. So basically, in this project, we're trying to propose a new training algorithm for large-scale machine learning, and we're trying to improve the stability of software machine algorithm, which is one of the most successful classification algorithms. This project is advised by Shelton, and I'm a PhD student in EC department, and I'm working on machine learning problems. So this is my outline, and I'm going to do a quick introduction and go over my method and experiments. So why we are doing this? The first and most important reason is large-scale machine learning. Thanks to next-generation sequencing, we're having larger genomic data sets. Also, there are very large clinical data sets. For example, Syria set contains over 8 million of records of patients over one period of time. The other reason we would like to do this project because most of current sequence solvers are not good for Powellism. Their algorithm is inherently sequential. The next reason we would like to do this, we want to implement online learning algorithm in our solver to capture the change in distribution of data, because learning is a lifelong process, and the distribution of data changes, response to the life change, and we'd like to adapt our training algorithm accordingly. The other reason is that with online learning, we are able to train very large data sets. In theory, you can train infinite size data sets, like train using mini-batch. So instead of parsing whole data set at once, we just fetch mini-batch by mini-batch and train them and go forward. Also, the other motivation is to train our solver using semi-supervised paradigm. This is a new paradigm of learning that we can use partial label-based data sets. So this is because the label data is expensive and noisy, because some experts should sit and label our samples and then put it to training algorithm. We can use this paradigm to train larger data sets and cheaper data sets. So existing SCM solvers, these are the three state-of-the-art solvers that, based off their characteristic, show them. The LibSCM is the most famous. It's not online. It's not good for parallelism. It can train nonlinear decision functions, and it's good for data sets up to 100,000 of samples. Other solvers are linear, which is the linear version of LibSCM, which is good for up to 1 million, maybe. And Pegasus is also online learning solver, and it's not linear. So when we are using linear and Pegasus, we are assuming the data is linear separate. And in this project, we would like to propose some solver to solve this issue. So in short, the SUMS tries to formulate the objective function as a mathematical optimization problem and solve it in the pre-model. And we solve it approximately to be able to trade off between accuracy and time. This is very important. Also, we use Newton's method to optimize this objective function. Newton's method is really good for parallelism because it involves matrix computation. Also, we use Huber-Law's function, which leads to very sparse solution, which is again efficient way to do it. Also, having implemented by Newton method, we can parallelize on different parallel computing platforms. And also, we implement online learning in the solver and try to learn from iDASH. So what is software information? The idea is quite simple. If we were to classify two classes, and we have plenty of choices, the best one, the best separating line would be the line with the largest margin. So the right picture is a software vector machine, which the solid, circle, and square are software vectors. And in the simplest form, the decision function is a line with parameters W and P. And finding the best, the optimal separating hyperplane is equivalent to solving this optimization problem, which involves this the phi, and phi is a loss function, which is really critical in characteristic of the solution. And we can use different loss functions to find different solutions, sparser or smoother solutions. So as I said, we try to optimize approximately. We just try to get the iteration to have a solution in limited amount of time. Also, Newton's method, it's an optimization algorithm that in each iteration it solves a linear system. So if we have n samples, we would solving n by n linear solving in each iteration. And these are the loss functions. The left one is modified least square loss function, which the shaded area is the area that determines the support vectors, number of support vectors, and as you see, the right one, the shaded area is quite small, so we produce much less support vectors than modified least square loss function. So implementing the Huber loss function, we have much smaller linear solvers, and since the computation costs for solving linear systems are cubic, you would get speed up as the data set is getting larger. And the online learning is really important because we are limited in terms of data sets. We would like to train the data sets by millivacs, and by doing this, we can process the data arbitrarily sized data sets, and we can also capture the trends in data by doing this process and process the custom data. And we also use large mini-batches to be able to do parallelism in each iteration. So Newton's method is basically just computational efforts in each iteration. Is just products, matrix inversion, and matrix vector computation, which are really good for parallelism. Also, it converges few number of iterations compared to gradient descent, which is hundreds, or stochastic gradient descent, which is thousands of iterations. So there's less dependency between iterations. We use large mini-batch to be able to exploit the parallelism. Also, at first I tried to implement it in MATLAB to get some result and verify my method and see how it works. I just implemented it in MATLAB and tried some Fourier sets to see how it works. The G50 is a synthetic data set that data set with overlap is not good for linear method, and the error rates are comparable to state-of-the-art solvers. Also, the news group is a sparse data set, which again, the error rate is comparable. Also, I'm planning to implement it in C++. I've already implemented in C++ for batch mode, single core and multi-core, and the next step would be implemented for online learning, mini-batch training, and other computing. And finally, I would like to extend it to semi-supervised learning. So in short, the proposed Summer vector solvers try to solve this objective approximately to trade off time and accuracy and the solution in limited time. Also, we use Hubert laws to find sparse solution and solve smaller linear systems. Also, plants can do parallelism because it uses Newton method and use large mini-batches in each iteration. Also, using online learning, we can capture the trends in data. And the future works will be applying to very large data sets and temporal data sets such as SEER data and other parallel computing platforms, semi-supervised learning, and finally, we'd like to propose a pilot version of this system solver. And I would like to thank Xiaochen and Shuang for their constructive comments and feedbacks, and also iDASH, BMI, and NIH for giving this chance to project. Thank you all, and question.
So can you speak a little bit more about the motivation for this problem?
Since the data sets are getting larger and larger, and the current system solvers are limited to hundreds of thousands of samples, we cannot process the data sets such as series or larger data sets to capture more complex relationship between labels and so many algorithms, many tasks require sample complexity of n qubits for some amount of error. So in order to reach some accuracy, you need more than 1 million samples. And this gives us flexibility to do it and learn nonlinear decision functions. Because the current largest scale system solvers are almost linear, and we are assuming, by using them, we're assuming that they are linearly separable. So by doing this project, we can process the data sets of infinite size. We can graph mini-batch and do incremental training of data sets.
Can you comment on the ability to your response on handling the temporal trend? Does that mean other solvers do not handle it, or what are the reasons for? Does it mean you rule laws, or what are the aspects that
the question is, are the other solvers able to capture temporal current? There are some online SQL solvers, but the online SQL solvers are all linear. There's no large scale online nonlinear SQL solvers. So they're either these are state of the art, the only online solver. The best one is Pegasus, which is linear. If you're using Pegasus, you're assuming the data is linear to separate, which is not good for many tasks. Thanks.
So we heard a lot about practicing analysis, and now we'll go through a series of presentations where we go through financial processing, personal income, and research. There's a UCSD grad student in linguistics with bachelor's degrees from UCLA in linguistics and Spanish and computer studies.
Hi everyone. So today I'm going to be talking about how people report being relaxed or stressed using social media, particularly by analyzing data from Twitter. And this is joint work with my mentor, Sylvia, and I think all are great. So first, let's talk about some basic facts about stress. I'm sure most of you are aware that people experience a great deal of stress at least some point in their life, probably more than once. There was a recent survey just done by NPR, Robert Wood Johnson Foundation, and the Harvard School of Public Health that found that just within 1 year, 49% of the people who were surveyed reported being stressed. And those that were surveyed that said they were in poor health also reported having this correlation of having a great deal of stress just the next month. And 54% of them who said that they experienced a great deal of stress reported that this was mainly due to having too many responsibilities and also due to finances. And just commuting to work was seen as a really stressful activity. So there's a lot of stress going on in the world. And it can have a lot of negative impact on different aspects of people's lives. So these people reported having negative impact on their family life, their health, their work life, and also their regular social life. So given that stress is an important health concern, we need to know how to identify the aspects of stress appropriately for this type of project. So we first need to know, where is the stress coming from, what are the causes of stress? It can be due to work or finances or so on. And also how does stress manifest itself. So there's psychological and emotional symptoms like being depressed, having anxiety, also being worried. There's behavioral symptoms like putting things off for the last minute, also smoking and undereating or overeating. And finally, there's physical symptoms where people have experienced headaches, ulcers, and chest pains, and other things as well. And lastly, there's ways to treat stress. So some people undergo positive ways to treat it, and some people undergo negative ways to treat it. So positively, you can relax. You can exercise and then spend time with your loved ones. Negatively, people engage in health habits that are actually, or bad health habits, such as over drinking too much, also starting smoking. So, given this information about stress, how can we use social media to identify health concerns related to stress? So the first question we have is there any populations that engage in positive or negative treatments for their stress, and if so, how are you not going to help them? In a similar vein, we want to know if there are areas of the health system that might be able to improve upon the health, which is, particular types of stress. And for those people who report doing a lot of relaxing activities, can these relaxing activities be translated as different treatments to people that undergo a great deal of stress? So the way that we started this project was first to collect an initial data set. The first step was to find user-defined topics related to stress, keeping stress in the last, basically using hashtags. And then once we collected all those keys, we got the same number from a 1% random sample of the diversity. We were using a keyword search to do stress for last. And so we had a total of 1,326 stress keys and 782 relaxed keys. And we developed a schema to tackle this problem and are in the process of finishing our annotation guidelines. And this work is based on previous social media and health work, and also health-related information, particularly about stress. Oh, sorry. And we manually annotated this initial data set to have a gold standard. And this will make more sense when I show you the schema. So here's the schema that we used for stress. So first of all, we had a stress classifier that had our groups and tried to separate them between non-stress and stress groups. So here's a negative example of something we would really consider as being really stressful. This one's talking about playing the game iDASH on the phone. Maybe it's really stressful, but obviously this is not something we're concerned about for higher, like something higher for health reasons. And then for the second classifier, we wanted to separate these groups that were about stress into first-hand experience and other groups. So we really don't care about what the people are talking about themselves. We don't really care about advertising to these articles. So here's an example of something that's not first-hand. So this is something talking about Skype therapy with stress, so we're not really interested in that. And then we divided everything up into the three aspects of stress, symptoms, topics, or causes, and also treatments or actions taken. And we also have this category because sometimes people talk about stress, but they didn't really say how or why or any other reason besides saying I'm stressed. So here's an example for the symptoms of psychological and emotional. So someone's talking about having nightmares. For the physical symptoms, someone's talking about having chest pains. For the behavioral symptoms, someone's thinking about going on an eating binge. And then for the topic of causes of stress, I'm not going to talk about all of them because of time, but here's an example about school. So I'm having a lot of quizzes and essays and regular school stuff. And then I have this temporal category I came up with that basically it's more of an abstract category and captures responsibilities, decision-making, changes, time limitations. So this particular example is about someone being really stressed out about having a short time to do something. And then for the action statement or treatments, there's a positive example of someone exercising, and a negative example of someone feeling the urge to post. And after for your last schema, it's pretty much the same. The first two classifiers are in the similar vein of the stress schema. This time we have different topics for personal experience. And these were, I forgot to say that these were all came up with based on important topics and also what was most talked about in our initial data set. So here's an example for drugs and alcohol. So someone's talking about using morphine to relax, which is kind of scary. And then there's this abstract category showing the cold water. And also these tweets are not usually kept. These categories are usually exclusive, so they can go on to one more categories. So this water category, it seems that there are a lot of tweets about people relaxing doing something about water, like taking a shower, or bath, or being at the beach or at a lake, or visiting the rain. So I came up with this category to explore more, and this is that. And then there's this rest category, basically about taking time off or vacation or just being at home. So it's just talking about how it's nice to take a break. Okay, so those are the schemas, and now I'm going to move on to the classification rules. So we have the goal of classifying stress and non-stress groups, and also classifying between the relaxed and non-relaxed stress. So we use the initial data set. So again, we had 326 stress groups, 782 relaxed groups, and we use this technical cross-validation evaluation. And we actually have extremely high accuracy with the SVM classifier. So we are going to be using this, I'll talk about it in the future as a requirement. And then also some linguistic analysis, those who are going to be developing our annotation guidelines right now. For the stress data set, we've actually found that 20% of those groups are in this men category. So a lot of people are talking about stress and not really saying how they're stressed or why they're stressed or what they're doing about it. So that's pretty interesting. And also, we still want this information if we want to know what kind of population are being stressed, but there's still a lot of information around giving us. And then we found that for the topic category, the largest one was school. So this might imply that the largest population talking about stress is all students. And for the last data set, we found that 20% of them knowledge was interested in abstract water category, which I kind of talked about a little bit earlier. and 6% of them fell into the drugs and alcohol category. And we can compare this to 4% that fell into this category for the negative action taken in the stress data set. So this is interesting that it shows similar proportion across the data sets, and there might be a similar population that is feeling stress in the negative way that we want to reach. So if we can, we just got a new data set on US cities, and they were picked by their stress ranking in the US. So this was based on the 2012 Gallup poll. But we see that San Diego is actually one of the stress city, which is interesting. And there were several million tweets per city. And first what we did was we used a keyword-based search to just find any tweets that had mentioned stress or relaxing. And then we applied the estimated classifier that I talked about earlier to figure out which were relaxing and which were actually stress tweets. This is an estimation. We haven't gone back and actually checked like how correct it is, but it's probably, it looks pretty good. And then we have a proportion here of the tweets found by the classifier divided by the complete data set. So if we look at the results, we see that of the proportion, we see that stress is talked about 2 times more than relaxing. And San Diego actually does have more stress tweets than LA and San Francisco. That's pretty interesting because LA is actually supposed to be more stress than San Diego. So that's going to be interesting to look into it. And then if we compare New York City and San Diego, we see that New York talks a lot about work, and San Diego talks more about school and finance. So that's also And then if we look at the relaxed tweets, we see that New York is more about being at home. The watch frequency distribution kind of represents entertainment, like watching TV or watching a movie. And San Diego actually talked more about the beach, and also they talked about college as well. Anyway, so to summarize, I talked about the schema we developed in the annotation guidelines, and the automatic classifier that we were using in order to improve the cognitive stress in the last use. And we applied this to the US cities data set. And what we want to do is finish this work that we're doing and submit it to the journal. Thank you very much.
This is really interesting in particular. I'm doing this presentation a lot, but because I always have this fundamental question, which is about whether the social media really a reliable source of identifying some psychological problems that really requires intervention. Do you want to know if this studies really in depth to see whether this quick messages or Facebook messages really reflect the psychological solution of problems?
Yeah, there's actually, it depends on what the problem is. There's actually been a lot of different papers like that. There's one recent paper about different groups of people who experience similar diseases like Alzheimer's and how they relate with one another and how that might be a treatment. There's a lot of stuff on track actually, including like groups. So this is more about trying to figure out like what kind of population is stressed, what kind of population is reporting on social media. So of course we have that bias of who's actually using social media and how you can reach that specific population.
When you were looking at these tweets, were you able to determine any sort of intent versus consequence as far as like the relaxation or stress from these actions? For example, the morphine tweet. I would imagine that somebody may be taking morphine for another reason, and then they're saying, wow, it worked, I feel relaxed now. But it's not that they're saying, I'm stressed, I need to take some morphine.
Yeah, so the relaxants don't necessarily imply that they were stressed before. It's something that used to someone saying, like, oh, you're just getting out of work, now having to go home and wash your dishes. So, like, there's that issue as well.
Speaking about the water category, we have a 2-minute break with the slider. Hillary is a graduate student currently attending UG December at Houston with a degree in master's, with a master's degree. This was her area studies natural language processing. She was working on collaborating and this project is being rendered by someone in humans.
Hi everyone, today I will present briefly the natural language processing to extract consecutive listening from. My name is Suri Yo. I'm a second-year graduate student from British Health Science University. I went to during this summer internship with Dr. Samdong and my co-mentor, Dr. Nashi. The aim of our project is to extract consecutive symptoms from clinical notes. Currently, the recommended diagnosis of cholestatic disease is based on presence of fever for more than 5 days and 4 out of 5 clinical features. Since these features overlap with many other diseases and are not typically present at a single time point, they tend to be overlooked initially, resulting in missed opportunities of treatment. In fact, 4 kidney patients lost their young lives in the past 20 months at Raleigh Children's Hospital due to late diagnosis as of June 2014. Since there is no existing NLP framework for to identify kidney symptoms, so we propose a template solution that will provide a systematic method to screen through narrative clinical notes to identify potential kidney patients. This is our general NLP framework, which contains 4 components: patient guideline, kidney symptom recognizer, visualization, and collaborative annotation environment. First, I will introduce our annotation guideline. The diagnosis of cholestatic disease is based on fever time, clinical findings. My presentation will focus on clinical findings. These findings are extreme changes like redness of hands or feet, polymorphous eczema, rash on body, conjunctival injection like eyes are red, changing lips oral cavity like have strawberry tongue, cervical lipidinopathy like patient's left side of neck was red swollen. Since there's no existing annotation guideline for annotate cholestatic disease, so in consultation with Dr. Jim Burns from Cholestatic Disease Research Center at UCSD and Raleigh Children's Hospital, and based on the paper, diagnose, treatment, and long-term management of cholestatic disease. Our annotation guideline team created this annotation guideline for identifying cholestatic disease symptoms in clinical tests. Our annotation guideline team contains 3 physicians, 3 computer scientists, and 2 employees. This is a screenshot of our guideline, which includes definition, patterns, both positive and negative examples of entities that we need to annotate. Next, I will introduce our kidney symptom recognizer.
This conference has reached the duration limit for 3 or fewer participants and will now attempt to close the conference. If you wish to remain in conference, please press any key now.
This is our general pipeline. The input of the system is clinical notes. At first, we split the notes into symptoms and run through our kidney symptom tables to identify those symptoms. Finally, we will visualize our data in very next way. The most difficult part of this pipeline is symptom pattern. At first, we only have 6 clinical notes to build our system. So we decided to use a rule-based approach, regular expression to build our system. This is an example from clinical notes. Today, hands and feet appear red swollen. The keyword here.
This conference has reached the duration limit for 3 or fewer participants and will now attempt to close the conference. If you wish to remain in conference, please press any key now.
Keywords here are hands and feet and red swollen. Hands and feet can be replaced by hand or feet. Hands with longer, longer. Red swollen can be replaced by red swollen. This is next example. Today we have noticed the blood keywords here are fluids. The fluid can be replaced by dry, red, green check. This is an active example that we will not annotate as a case symptom. No rush on hand or feet because there is no example of rush on hand. The note can be replaced also by
This conference has reached the duration limit for 3 or fewer participants and will now attempt to close the conference. If you wish to remain in conference, please press any key now.
And the rush can be replaced by edema and arrhythmia. after we identify the symptoms,
No longer report. Please stand by while your recording connection is established.
after identifying those symptoms, we want to visualize our results in our network. So we create a web-based application. Guarantee the security of our data. User need to connect to iDASH VPN, and username password are required to log in. After login, you can see our application. User inputs the info nodes on the left side of the screen. Select the button, drop to timeline, and display the info nodes. Calculate the front end of this application with HTML, CSS, and JavaScript, and accurate the backend sensitive header using Python to combine the front end and with HTTP. This is a result example from our application. Thread lives in oral cavity, thread have liberalized injection, brush on her arm like the muscle. Neck has the pencil is frequently healthy, hands video is lower contribution. Collaborative animation environment. So after to measure the performance of our own system, we need to compare our results with standards. This is multiple standards here, so when our physicians have to manually annotate and create a reference standard class. So this set has a zero quality animation environment within iDASH. The three divisions create the reference standard. Currently, 30 identified nodes from Ready Treatment Hospital from This is the existing annotation tools that involves the division to annotate, named the graph. Preliminary results. 8 identified nodes from Ready Treatment Hospital are manually annotated by the division head. 6 nodes are applications, 2 nodes are non-applications. There are 64 mentions of theory clinical findings in this base node. We use precision record S4 to measure performance. From the table, we can see that the prognosis at is 0.74, Taiwan junction is 0.7, which our cavity is 0.87, and extremely changes in circuit and conflict are really low. So we look at data, and we found there's a lot of false negative extreme changes, which means they are facing a system failure and for the critical immunity, because which means they are not these symptoms, but we only have these symptoms because we have an application already. Because we're looking at the gene data and analysis will improve it. The challenges here are first is microbiology and second is symptoms. Some of my work, this is a big project which involves many people. I involved in this project and like animation guideline, collaborative animation environment, and I'm mainly focused on these symptoms and method and visualization. Internship experience. During this internship, I contributed to build the personality framework to identify cognitive symptoms, and I contributed to develop a bio-NLP application from scratch. And I also learned how to cooperate with online experts to create communication guideline and set up a collaborative environment communication. Our project, the aim of our project is to build a general NLP framework that has our future direction are design our fees and hybrid evaluate based on more clinical notes, and after we get that performance, we will find our work in during some competition. So here I have that our annotation analysis, area relates to another are small. Our annotators area will include their own needs. In the article areas, we have data, CPR, and iDASH. naturally emerging with the development of all the testing technologies, like iDASH, and also iDASH companies.
So the current code, probably I missed if you explain what those characters mean in which three. Yeah.
Yeah, because animals are constantly based on liver time and clinical balance. So like blue molecule is affected, which means liver time. And there's a pink label means liver. And the brown one dash means promoter. So this annotation tool, so the doctor will select the word and select the
so you assign the color to specific keyword.
Yeah.
And you get it together.
Yeah.
Hi. I'm glad you're doing this because Kawasaki's, I'm an emergency medicine physician, and Kawasaki's disease is one of those things that, you have to think about in every little thing that shows up on your door with a fever, but, by and large, it's going to be very hard to find because it's going to be some virus in there or something like that. However, I was wondering if you guys, once you develop your model, if you're going to be comparing it to, because frequently, we're going to be writing notes on these patients, and if we don't think these, it's not going to be charted that way. So these notes are based on patients who have already had the diagnosis made, I'm assuming. So it might be helpful to compare, once you have your model about it, compare it to notes where the disease diagnosis was missed initially, either in the clinic setting or in the emergency setting, and kind of compare the data to see what exactly was being missed out of those notes. Because if you want to catch the Kawasaki's disease presentation, you're going to be, so for example, when I write my note and I'm not thinking about Kawasaki's disease, there has to be things that I'm typing that I'm not thinking about, and it may help that the system can recognize, hey, you have 4 out of 5 Kawasaki's disease criteria in your note. Did you think about it? Something like that. But I was wondering if that was something that was going to be developed later on in the project.
Our next speaker is Susie Peel with identifying temporal relations in clinical notes. She has a bachelor's in engineering, computer science at Shandong University in China, and is currently a second-year PhD student in computer science at the University of Pittsburgh. Her mentor is China.
Hello everyone. Today my topic is identifying observation. My mentors are Dr. Matthew and Summer. I'm a PhD student in computer science and medicine. Our only goal of this project is to identify the timeline of patients. It will help to visualize the notes in a more structured way, and it might also help for demand purposes, like search for similar clinical temporal patterns or predict disease rates. Previous work in general domain genes has present temporal language in 2005, and not until recently, Sloan and Skyler extended to clinical domain. Generally, in clinical domain, temporal relations are defined as a relation between two clinical events, or between the clinical events and the temporal relation expressions, or the clinical events and the location time. For the types of temporal relations, it could be before, during, after, continuous stop point, or end point, and so on. So really these problems could be breaks into 4 subtasks. First is to tag clinical events, and the second is to tag temporal expressions. The third is to connect the clinical events and the
temporal expressions. And finally, we'll resolve the chemical tempo. In this project, we started two data sets. The first is usually health heart disease risk factor data set. And second is from UCSD ready children's hospital cosmetic disease. So for the first heart disease set, the target events could be the heart disease risk factors. For example, diabetes, hyperlipidemia, hypertension, obesity, or medications. And the target temporal relations would be the relation between new events and the location time, which would be before, during, or after. We'll follow this process first with the temporal events. Thanks for my reports, our group has already developed biomapping titles to this conditional random fields and solo groups. In the next step, let's have temporal related expressions. I utilize a tool developed by in 2013 called MyTime. It will recognize the time, date, duration, and frequency in the task. In the next step, I will normalize these temporal expressions with respect to the node creation time to before, during, and after. The third step will connect the relation between the confidence and the temporal expression. In this set, all the three types of temporal relations are not mutually exclusive. So I decided to build three classifiers, one for each type of relation. And I use a linear complexity for this classifier. For the features, I choose to use part please. Which would indicate the tense or the modularity in the sentence. I also use time-like sequence like before, during, and after. And also, I will utilize the text structure such as the node section titles. Also, we'll use how the computer events are expressed in nodes, like the quantitative evidence, or it could be qualitative evidence, or diagnosis of disease or disorder. Next, I will use this processing pipeline to generate the features I mentioned about. For the experiment, I split the whole data set into almost 50% training and 50% testing. And for the result, as errors in the result of biomapping tagging to include the event tagging errors and temporal relation errors. And we want to find out the errors due to the temporal relation errors. So I also show the results using the gold standard. Event taggings in this case, showing this table, the event taggings are perfect and error associated due to the temporal relation classifier. So the temporal relation expressions will reach about 90% in FR measures. So this is monitoring the next data set is a cosmetic data set, and in this data set, our target events are the symptoms of cosmetic disease. I only focus on the prolonged fever symptoms. In this case, we would like to find the fever and the duration of the fevers. So we define the temporal relations as the relation between fever and the temporal expressions. Then we'll follow these four steps. First, we'll tag events. I use mentions of fever as keywords of the fever, like fever, fibro, and and also we'll include some positive like scarlet fever, heat fever. And then we'll also tag this on the temperature above the threshold. For example, for investments, we'll just tag the fever. Investments, we'll tag high fevers and temperature 1 or 2. Investments will exclude the scarlet fever. In the next step, we'll tag temporal expression. Then we'll use a tool developed by in 2013 at time. We'll tag date, time, date, duration, and frequency. For example, in listeners, we'll tag November 26. In listeners, we'll tag 6 days, exactly duration of the fever. And in this sentence, you will type the scenario. In this sentence, you will type like at the time of the nation as a reference. In the third step, we'll connect the temporal relations. Because currently you only have a node, and so we just start using the set rules like when inverted temporal expressions between the sentence or in the adjacent sentence view, or come up with more specific strategies we quickly and more data. For example, in this sentence, we will connect the fever and the October 26th and mark it as a start point. In this sentence, we will connect 40s and high fevers and mark it as the duration of fevers 40. In this sentence, we will connect fever and for 2 days. As this is a negation statement, so we'll mark it as the end of the fever. Hopefully we could grab this fever timeline, recover this fever timeline from the notes, and the temporal experiment is traveling. As far as we're concerned, the challenges in this project we had quite a lot of data statement, negation statement, and also the dimensions of fever and the temporal expressions with bimodal sentence. For example, in this sentence, this is a static statement that we cannot use this to recover our fever time. In this sentence, this is a negation statement, and we need to recognize it and get an endpoint for it. In this sentence, the mention of fever and the time is spanning two sentences, and we need to use some reference resolution in order to get the reference time of the fever. To summarize, in this project, we identify temporal relations from pre-tested nodes, and we apply it to RD-series vectors and concept disease. For future directions, the first thing we do is to model our annotated data set of concept disease, and we will deal with negations and have data experiment. Also, we'll deal with one more step. It's like resolve the timeline within the temporal relation. I want to thank all our team members for the annotations and trailers of videos. We'll also thank Dr. Jenkins, our mentors, our advisors, and government interns, iDASH, and team government, and we'll also thank
Questions?
Question. Sometimes the temporal relationships in nodes, I'm sure you recognize it, is pretty, there's a lot of uncertainty even when the clinicians put in the temporal relations. So, for example, a patient may come in and say, I've had back pain for several months or something like that. We don't have an exact value. Have you guys thought about sort of how you plan to visualize that type of inexact sort of start or duration of symptoms, where it could really range, say, several weeks, several months, several years, something like that?
Yeah, so currently our system with the like exact dimension of the duration. We haven't reached ourselves to deal with it, say, like several weeks or several months.
Okay.
So for fever mentions in the fever notes, for example, the notes will always say some exact time of the duration because I think this might be a key symptom, so the physician would try some exact date.
Thank you. presentations related to NLP from Mark Nesbitt. Learning discourse relation to biomedical text as a national linguistics from UCSB and bachelor's in linguistics from Harvard with measures
So this is a joint work with someone. So one problem that is very difficult, but also very desirable in language processing is extracting discourse coherence relations, which are pieces of information that span multiple sentences. So this is desirable in a lot of biomedical tasks. So these include things like question answering, information extraction, document summarization, and you can think back just to CC's talk, which you mentioned, problems extracting information spanning multiple sentences. This could be a potentially useful approach to that. So what do we mean by discourse coherence relations? So here's an example from biomedical text. The URCA1 gene induced significant rescue of cells in the thymus, but produced little recovery of cells in the peripheral lymph node compartments. So we can break this down into two semantic arguments. The first one, induced significant rescue of cells in the thymus, and the second one, produced little recovery of cells in peripheral lymph node compartments. And these are joined by the discourse connected butt. So in this case, this is a contrasting relationship signaled by the connected butt. And you can imagine a lot of different kinds of relationships, parallelism, causality, and so on. In fact, there are 31 standardly used coherence relations. This is a scheme of biomedical coherence relations adapted from schema used in the past. So our task is given some biomedical document, before notes, or any other kind of biomedical document, extract the coherence relations on that. So what kinds of features do we have available for the task? So one obvious one is this discourse connected butt. However, in many cases we don't have that luxury, and the connections are just implicit. So the problem is to identify, in this case, induced significant rescue of cells in the thymus as standing in a contrasting relationship with produced low recovery of cells in peripheral compartments. So what kinds of features can we use for our machine learning task? So one class of features that has been proposed before is grammatical syntax. So the linguistic substructure of the arguments in question. And this has been proposed in the context of newspaper text, but not by that. So what does this look like? So returning to our example here, we can actually put up the linguistic parse trees for each of these arguments. So on the left side, we have induced significant rescue of cells in thymus, and on the right side, induced low recovery of cells in peripheral compartments. So if we actually look at these parse trees a little bit more closely, we'll see that they're actually identical. We won't see that. They are identical. So in this case, we have identical syntax in the context of a comparison or contrasting semantic relationship. So this is an argument for syntactic structure providing some kind of useful cues to the overall semantic relationships. So what kinds of features can we use given that? Well, we can actually break these trees down into the subtrees. These are also called rules. So for example, this rule, PP goes to prep NP, could be a feature in our machine learning task. And this is the approach of Limit All 2009, although not in the context of biomedical text. So in terms of this project, we have two goals. So one is to evaluate the syntax feature in biomedical text for the first time. And the second is to actually develop a new feature, syntactic recurrence, that we think can improve over the basic syntax feature. And this is something that hasn't been developed in any kind of text so far. So let's take the first sub-goal here, evaluate the syntax feature in biomedical text. So our data set is the biomedical discourse relation bank, which is the corpus of 24 full-text biomedical articles from the genome corpus, almost 5,000 sentences, almost 6,000 annotated relations, 3,000 of which are implicit. And we're going to be focusing just on the implicit relations. So given this data set, we run it through the state-of-the-art biomedical syntactic parser from the Costing content. From there, we
develop our features and learn our machine learning algorithms, and finding out the classified relations according to those 31 classes that I showed a few slides back. So for machine learning, we use SDM, in particular SDM multi-class, 31 classes in a linear ML. Our training set consists of 20 of the documents in the corpus, which is over 2,000 resource solutions, and the test set is the remaining 4 documents, which is about 600 resource solutions. So here are our results, and these are just for the syntax feature. So on the y-axis, I have classification accuracy with a baseline of 28%. So this is based on majority class. So if we just, for algorithm just shows the most common class every time, you get 28% accuracy. And on the x-axis, I have the number of syntactic rules that we use as features in decreasing order frequency. So 1 means that we're just using the most frequent syntactic rule, 25 means we're using the 25 most frequent syntactic rules, and so on. So here's the classification accuracy on the gene biomedical corpus using the syntax feature. And you see that there is some nominal improvement over baseline. So you go from 28% to something like 29% using the syntax feature. So the syntax feature does seem to have some useful information in it. So now we go on to the second part, which is developing the new feature, syntactic recurrence, for learning resource solutions. So what does this mean? So in this feature, we leverage the temporal distribution syntactic rules to the document. So if you think back to a syntactic rule, like PP goes to pref NP, we can actually annotate a document for where that rule occurs. So in this case, that rule is used twice in the document, both tends pretty close to the beginning of the document. And so we can measure that distance and normalize it. And so we have a relatively short syntactic recurrence to value these features is relatively low. You can also imagine another document where these rules occur at a greater distance. And so in this case, our syntactic recurrence feature value is going to be significantly higher. So let's see how this feature does on the same pass. This is again the biomedical discourse relation bank, classifying into 31 classes. Here's our baseline syntax feature. And here are our results using syntactic recurrence. So we find about a 4% improvement over baseline. So this is substantially better than using just the syntax feature alone. And I can also talk about why this should be an interesting feature from a kind of linguistic and cognitive standpoint. If anyone has some questions. So to summarize, we provided the first evaluation of syntactic features for learning coherence relations in biomedical text. And we've also introduced a new feature, syntactic recurrence, that has not been tested anywhere before, that improves on that state of the art. And we have plans to evaluate this as well in descriptive text and other genres to see what kinds of challenges might be unique to the biomedical genre. And we actually still have a lot of tricks up our sleeve for improving the feature. So if all goes well, we're hoping for a potential submission to JDI. So thanks to my collaborators and funding agencies and to you.
I have a question.
Yeah.
When you were showing accuracy earlier, what exactly measure the accuracy of?
So accuracy is the percentage of correctly identified discourse solutions out of that 31 set hierarchy. So that is on the lowest level. So there's 31 classes. But if you actually get back off to the higher level hierarchies, then that can go to like 12 or 4 classes. And so we're going to try that and set higher accuracy there. And that might be enough to be used.
And it was correctly detecting what of the modifiers were in place?
So it was not using the connectors model. So we're using only the implicit relations. So we have clause 1, clause 2, and we want to identify that this is a contrasting relationship, this is a causal relationship, what have you. But it doesn't use any explicit connectives or anything like that.
Okay, thanks.
So this is run on the biomedical, the articles in the database, like these, and they already passed sort of editorial phase where somebody actually made them good English sentences.
Yes.
I'm just wondering about like clinical notes, which sometimes don't have the same rigor of syntax and spelling, etc.
Yeah, so this is actually a notoriously difficult problem, even in polished editorial text. So kind of as a first pass, we're seeing what we can do in that genre. And then I think another logical next step is going to be what can we do with genre clinical notes, especially addressing the challenges that CC mentioned in the last one.
So we continue with implementing private performance programs from which my student who was a third year edited at Department of Computer Science, Riverside, 5 years from University of Virginia and master's programs. His mentors are Paul Parkinson.
Hello everyone, I'm Steve Cook, and I'm going to do this work on genomics pipelines and their use, how we're going to use these to hopefully provide a lot more genetic data in the hands of medical professionals who need them. This is work with my mentors, Junior McKim and Dr. Claudia Farkas. And so let's start by way of introduction, why do we care about genomics? What we see here is a slide from the 23andMe project, provided you registered before the FDA. So, the information on the left side, these secrets are not allowed to report anymore. But this is an example of the kind of data we can glean, these very different statistics, that we want to be able to get fast and affordable access to for clinicians in a medical setting. So things like drug response, carrier status, and risk can be very useful evaluating patients. So a very short crash course in genomics here. Inside the cell, there are 23 chromosomes. Each of these chromosomes is composed of tightly bound DNA, which is itself composed of the four molecular letters, A, T, C, and G. There are about 3 billion of these base pairs if you lay all the chromosomes out from one end to the other. Now, a small fraction of these, 1 to 2%, actually code for proteins. They're transcribed within our cells into the proteins that give us our function. This subset is called the exome. And so it's much easier computationally to examine the exome and still get lots of very important information from it. So that's what we're going to be looking at today, is exomes. So how do we figure out what someone's exome is and how to get it into a digital format when we can run computational analysis? So current next generation sequencing machines will fragment someone's DNA, replicate it many times over, and then attach adapters, scan it, and provide a 100 gigabyte file or more of all of the DNA information in a file format. So now it's up to us to then take this and figure out how to take all these little pieces and put them together. Each piece is only on the order of about 100 base pairs long. We're trying to license 3 billion pair reference. So looking at this in a little more detail, we see these small sequences here. We're trying to align them against the reference genome down at the bottom. So it's a very big jigsaw puzzle we have to do. But it's not that easy. Not everything is going to match perfectly. There are errors in the sequencing equipment. The person's data might be very different from the reference we've collected. They might be missing things, they have extra things replicated. So it's a very difficult problem. It's complicated statistical approaches in order to deduce what the actual, in order to do this assembly correctly. So once we have this assembled, and we don't even know if our assembly is right, now we're looking for variants. On the left, you'll see homozygous variant, where every single marker for that individual has a flip, a SNP, a single nucleotide polymorphism, at that position. On the right, sometimes they have it, sometimes they don't. And this can be very complicated. It can be due to sequencing errors, it can be noise. And we need to say, okay, which of these are going to be known markers for dangerous diseases and medical conditions? Which of these are noise? Which of these are not? And that's the challenge we're looking at. So we want to create a software pipeline that can do all of this work to go from those fragments that the sequencing machine gave us to something like the 23andMe output slide I showed earlier, with very little need for advanced computer science techniques on configuration. We want to make this something that the person can use. We want this to be fast. So we want to do a human exome on the order of several hours, so we can get the information as quickly as possible in a life-or-death situation. We want it to be accurate. We don't want too many false positives or false negatives when we're predicting what they might be at risk for. We want this to be affordable. We want to do the data processing for one person in the order of $10. And finally, as I just mentioned, we want it to be easy. It should be something that people who are not, who don't have strong computer science backgrounds can install and run. So we set out to evaluate some of the current systems out there and try to make them work for us. And we learned some things along the way. First lesson is that the existing software pipelines are, generously speaking, difficult. What you see here is an email chain started on July 8th with one of the developers of a popular pipeline. And it took 62 messages back and forth since then to get this thing configured and set up. Along the way, we found bugs in the code, parser difficulties, software dependencies, all manner of things made this as difficult as absolutely possible. I was shocked. And we're still learning more. The second lesson is that ground truth is still kind of the Wild West. What you see here is a many-way Venn diagram between several tools for doing the variant following. All of them, you'll notice, report variants that the other ones don't. So everyone uses a different underlying statistical model to do variant detection with varying results. These are very recent papers. SM I think just 2 years ago. This is also an area under development. So we think that a good pipeline should be able to support not just one, but many of these interoperably. So the user has a choice of which one they want to go with if they decide that, say, G18K provides the best benefit for what exactly they're looking for. So after all this trouble, we got a pipeline working, basic one, and we compared it to chromosome, and looked at the chromosome 1 at the number of SNPs discovered. It passed most of them, and what you see in the middle column is how many of these were in the reference database that we've seen before. And we saw that for what we discovered, roughly 10% were novel for this individual that we tested. We compared our pipeline against what I call a SAM-tools pipeline. We made these steps manually with command line tools. And we found a good deal of overlap in the number of SNPs discovered. Again, as we saw earlier, it's not uncommon for there to be great deal of differences, but this at least gives us some confidence that our pipeline is similar to other existing tools out there. So we looked at accuracy a little bit around the surface. Now let's look at the single exome time and cost. So our pipeline takes 5 hours and 20 minutes to run on a powerful server here at UCSD. A published one takes 10 hours, and extrapolating these costs to a similar power of Amazon machines we rent from the cloud, we see that our cost is roughly the same, on the order of $8 for just the CPU processing time alone. I did some extra calculations for the S3 storage cost and the EBS, the volume store cost on Amazon, which is all the space you need to actually store these hundreds of gigs of data. And I came up with a rough number of about $20 per exome. So we're pretty good on our target of money here, too. To summarize the project and look forward to the future. So this summer, I configured a working variant pipeline for variant college. It was a very difficult, very manual process. I have a CS background and many, 2 months at my disposal to just focus on this project, and it was still extremely challenging. I don't see how anyone who's a geneticist with very limited time and resources will be able to do this. Even published results did not work as intended. Another one, you kick it off on Amazon, and the idea is that you would give it your credit card information, and your genetic data, and it would rent servers as needed to process the data and give you the results. After 4 days, it was still charging us money, still renting servers, but it didn't actually provide any data or offer that it seemed to hang. So never mind the Bitcoins for all we know. So anyway, these published works do not work very well, and there's a lot of room for improvement for these tools that are very important. Some more flexibility is needed as well. We want something that can be configured easily, and also are multiple different variant calling tools under the hood, since there's so many approaches out there, and no one seems to be sure quite exactly which one is best right now. We also deploy for different use cases. We went outcall scripts for organizations such as the VA Medical Center that are not allowed to send the patient data outside of the system. They can't upload to Amazon. So we want to give them something they can download and run this on their own servers locally, and then they won't have that problem. Also, we want to try to cut Amazon cloud computing. Let's say there's a small lab that can't afford its own hardware. we want them to be able to use this Amazon system, and then on the order of, say, $20 that we've seen, they can start getting into Exos. Finally, contributing back to the community. With all the bug fixes I found, I got a lot of thanks and everything from some of these developers, and we think that making these tools better will eventually be in benefit them. To finally conclusion, I'd like to say that we found lots of room for improvement, and we currently have our own tool under development. We think we'll solve these problems and provide great benefit to the community, especially in light of the ever-increasing number of genomes and the terabytes upon terabytes of sequence data being generated. With that, I'd like to thank my mentors and the my staff, interns, and the program, and open up for questions.
Remarks. So let me ask your personal opinion about 23andMe. How far is it from providing information that could be helpful?
Well, with them currently, it's a full, they do the sequencing and everything. So we're envisioning more like a medical center that has its own sequencing department, and they can actually do the wet work themselves. It's the DNA processing after that is more what we were looking at in this particular instance. Part of the reason there's a controversy around them was because they were trying to provide this medical data without really being upfront about just how wishy-washy some of this is, the statistical confidence intervals, and how much of this is still unknown. So I haven't tried it myself, but my understanding is that they don't report very much on what algorithms usually do, but there's a kind of a lack of transparency. And we want a tool that will provide every single step of the way that we configure, and you know exactly what's happening end to end. Also, faster and more performance setting. If you're in a clinical setting, you understand how it would be, whatever it takes to do the space log than the other part. Thank you.
Our next speaker is Alexander Richardson, for about 10 minutes for medical concept hierarchy development. He's going to be doing the last database. He's an undergraduate, 60, and he's working towards a bachelor's in computer science with specialization in bioinformatics.
Thank you. Hello, I am Alex Richardson, and today I'll be presenting on my summer work on improving search results for a medical studies database. The title of my presentation is Concept Hierarchy Development using UMLS or Vendisco. My mentor for this assignment was Yomi Kim. I am currently a student at UCSD pursuing a Bachelor's of Science in Computer Science with specialization in bioinformatics. So a little background information. Vendisco is a search platform currently being developed at the UCSD Division of Biomedical Informatics. Its purpose is to improve the search results for the database of genotypes and phenotypes through concept-based search. The database of genotypes and phenotypes is an archive containing studies on the interaction between genotypes and phenotypes, and the variables of these studies are standardized in a separate process called PFinder for use with Vendisco. Vendisco currently only supports synonym expansion, but we are currently in the process of implementing hierarchy expansion functionality. So as you can see to the right of the search bar, the Vendisco currently does support concept-based search, except currently this is limited to synonym expansion. So for example, if a researcher wanted to find studies related to heart disease, it currently would expand the search to include results for cardiac disease as well as cardiac disorder. We would like to improve the search results to also include medically related terms such as pericarditis or myocardial infarction with this to help further aid researchers. So our goal is to implement this hierarchy-based expansion of the searching. To do this, though, we first needed to develop a hierarchy for the expansion. So we decided to use the UMLS and create a subset hierarchy from it. This is just an example of the current hierarchy we have in progress. It needs a bit of cleaning up, but it gives you an idea of behind the scenes of the hierarchy expansion. So UMLS is a unified medical language system. It's a compilation of more than 100 medical terminology vocabularies and also contains relationships between these medical terms. I use relationships for harvesting the algorithm, for harvesting relationships to build the hierarchy. So the three algorithms that I've developed, first is relationship harvesting, followed by node legitimacy testing, and finally redundancy elimination. So to begin building a hierarchy, we first have to harvest all the relationships related to the input GUIs from the UMLS database. So we first begin, red ovals represent the input GUIs we start with. We would query their parents from the UMLS database and save these relationships. The parents then become children, and we would query their parents and save these relationships as well. The process continues until we reach a specified top hierarchy concept or until we reach the top UMLS database. So now we will have a hierarchy implied by the relationships we have gathered, except it also contains a lot of excess information and redundant relationships that need to be cleaned up. To begin the cleanup process, we use node legitimacy testing. So there are some nodes or input GUIs who have no natural relationships to a top tier concept, such as these. And then there are also nodes which do not follow. We have a policy that each node must have 2 or more children, and these nodes must also be removed. But as you can see, one of them is an input GUI, which must be in the final hierarchy, so it is still considered valid. So to start, we first remove for the nodes that don't reach up to a top tier hierarchy. We simply group them into a miscellaneous category to be later hand mapped out by a medical professional. And then for the nodes with less than 2 children, we simply create a direct relationship between its child and its parent. Now we need to reduce the redundancy of relationships. A relationship is considered redundant when a child has both a direct and an indirect relationship to a parent. These relationships must be eliminated to improve the search results. So then after this occurs, some nodes will now have less than 2 children and violate the 2-child policy, so node legitimacy testing must once again be performed. The current status, we are currently still optimizing the cleanup process, specifically the node redundancy elimination. We are using a training set of 50 cardiovascular disease concepts to develop the algorithm. These are chosen because they are fairly straightforward and they have possibilities to build a hierarchy out of. Some of the challenges we face, there are many inherent problems with the UMLS database itself, which is one of the reasons we use a subset of it. There are concept hierarchy loops, such as venous thrombosis is a child of thrombosis, which is a child of vascular disease. But for some reason, vascular disease is a child of venous thrombosis again, which causes problems with the algorithm. There's also concept islands within the UMLS database in which these concepts have no parents, so they are simply added to the miscellaneous category to be hand mapped out later. Redundant relationships are the current issue at hand. We are trying to clean up, and then we will need to test the robustness and scalability of this approach to the actual database of genotypes and phenotypes. So in summary, I have been working this summer on improving the concept-based search of the Fendisco search browser for the database of genotypes and phenotypes. Currently, we are implementing the hierarchy-based expansion for the search results, and we are still in the process of cleaning up the algorithms for the redundancy elimination. For the future, we hopefully plan to soon apply this to the actual phenotypic variable concepts in the database of genotypes and phenotypes. So I would like to thank my mentor, Yoni Kim, collaborators Emily Fireman and Edna Shenby, as well as all professors, staff, and interns, iDASH, DBMI, NHLBI, and the National Institute of Health. I will now take any questions.
So, do you go up to the top node of the hierarchy?
We actually use a hybrid method in which our collaborator envy creates so top-down hierarchies, which my algorithm builds up to.
Thanks everyone. We have our last speaker today, and we will also see that last and we'll have 30 hours in very brief close remarks. So Wendy Gautier is a UCSD graduate student in computer science, who also does a master's degree here, and he is a Robert.
Alright, well, thank you for the introduction. So I will present the last topic in this session, which is about outlier detection in the clinical course of the intensive care patients. So this project consists of Robert Dunter, my mentor, and myself. So I'm PhD students here at UCSD in computer science. This is my summer project. And what is the initial idea behind this project? Well, we have some clinical courses that are a bit unusual or outliers among others. So let me give you a simplified example of this. So we have some patient's condition that might either improve with the given treatment or sometimes decline despite the treatment. And this is the common case, but sometimes some patient's condition can maybe improve at first and then suddenly decline and then maybe improve again or not because the treatment is changing at the end. So the point is, those cases are outliers. And detecting outliers can be very beneficial to get better understanding of the diversity of cases, the diversity of population. It can be also very interesting to detect outliers. If we have a robust model, we can detect these outliers during the course of treatment and therefore have an early detection of issues during the treatment. And it is also interesting to identify all these cases, to review them for potential errors, which is the focus on our study here. So to identify these cases, for experts to review them. So the point here is that some of these cases might already be good candidates for you, because maybe the patient unexpectedly died, or something like this. But a lot of these cases will never really be reviewed because there are so many cases out there. So our goal is to restrict the number of cases to only the potentially most interesting one, because they are unusual, because there is some valuable information inside. And so experts can review them to find errors maybe, or find, because there's like some misdiagnosis in the patient, or maybe just find a patient that's an unusual condition or unusual response to treatment, and learn from that and improve maybe future care of patients. So we choose to focus on intensive care unit mostly because there is a database available. It's a very nice database because there is a very large number of patients, and for each patient there is also a very large number of clinical features available that we can extract. So from this database, we build this project around three main steps. The first one would be to select a group of patients with a similar condition, so that we can get a homogeneous set of patients. And then, try for each of these patients, try to represent their evolution over time based on these clinical features from the database. And maybe try to find sort of typical case, typical treatment that most patients fit in, but some of them don't, and those would be the outliers. So our approach to that, our first approach to that, was first to choose the patients based on their DRG code. So this is a code attributed to each patient at the time of hospitalization. It's mostly for billing and insurance purposes, but it can group the patient with similar conditions. And then we applied a method that we found in the master's thesis from MIT that gives us a list of clinical features that are really relevant and give really good information about the patient's condition. And so we extracted, we extracted all these features at different points of time, and then apply a clustering algorithm so that we will get different, a small number of patient states. And then each patient will have a set of states. So as an example, so from these ideal cases that I presented at first, each one will be represented by a sequence of states, a patient moving from one state to another. And hopefully the outliers will be represented by a very unusual sequence of states. And so try to detect that we want to analyze all these set of states and compare them. So either compare them as sequences using algorithms such as dynamic time coding, for example, or we can also analyze them as a set of features by just counting the number of states, within states for each patient, and apply an outlier detection algorithm. So the point is to get a similarity index, so that each sequence of state, each patient will have an index that will tell how far it is from all the other index, and then one patient will move a very large distance to others would be an outlier. So far, we extracted the patients from the database using those DRG codes. We extracted all those clinical features for each one of them and applied a clustering algorithm to get a few patient states. We tried to experiment and so maybe a different number of states. And then we apply some different methods that I was talking about to try to classify the outliers, try to get the similarity index I was talking about. However, we still need to get all those patient cases to be reviewed by clinicians probably to label or partially label the cases as being maybe outliers because of an error or not because of an error and not an outlier. So we need to get our gold standards in order to evaluate our preliminary results. And that will also open the door to maybe more algorithms for supervised or semi-supervised. So the current limitations of this method is that the database has some missing data and a few wrong values that might affect the accuracy of the clustering algorithm. Also, clustering is as discrete and symbolic values as opposed to a continuous numerical value, and this is not a really good fit for a lot of algorithms for analysis. And finally, the states are theoretically very nice because we can say, okay, one state is patient is in good condition, another state is patient is in bad condition, something like this. But it might not necessarily be the case. It might not be as accurate. And so for the future, we started to do that is to, instead of clustering, maybe try to calculate an index from those clinical features. This index could be based on Apache score or SOFA score, which are indexes used in ICU to quantify the severity of the illness. So they are used already, and So this is like an example of a SOTA score calculated for each day for 2 patients. And so you could plot some curves based on the scores and try to analyze the shape of these curves to determine outliers and identifiers. Alright, so I would like to thank my mentor and all the people who helped us for this project, and I will now answer any questions.
I'm wondering when you calculate the time interval that we consider for the 1 day or like or by day or by hour, and when you define the outlier here, so in case the patient takes like wrong medication or overdose, so this can be called as an outlier.
Yes. So you're asking about the okay. So we define this different bonus of time for states. So we use an accuracy of 1 hour or 30 minutes, something like that. So can you repeat the second question?
Yeah, the first question is the time interval. Yeah.
Yeah.
By hour.
So it was around an hour, but we had to experiment with different time periods. And for the index calculation, for example, it was 1 day. But we might use that for a few hours.
And the second one is about outlier definition and
Yeah.
Give us what is an outlier if the patient takes different medication or like.
Right. So this is where we need maybe some expert review that will try to help us identify what are the cases that have a lot of valuable information, because the treatments or something was not usual. Like the reaction to the treatment was not the one expected for this particular condition, or maybe the condition was not the one diagnosed. It was not the one from the first diagnosis.
I have often to support this seminar. It has been a great pleasure to work with all interns in the summer, and I thank all mentors for their support and to making this internship symposium so successful. And furthermore, I will very grateful to the iDASH and the UMI staff, without whom our program couldn't be so efficient. Finally, this important work couldn't be happened without the continuous support of our National Institute of Health. Thank you for making this experience possible for our scientists at Japan. And as per tradition, I included a couple of photos of the work hard and play hard environment that we created at UCSD. You can see some interns working on the project either independently or collaborating on it. In the top 2 photos and in the bottom 2 photos, you can see the result of the successful iDASH solidarity meeting and iDASH achievements. And thank you again.
So I too want to thank everyone for the interns and collaborators and mentors for putting together a well-prepared set of presentations. I also want to thank Morgan for her help shit together, Greta, Elizabeth, for having all the details for organizing like this. The staff here also seeing the presentations, and this is very important. We do expect to see the papers that are coming out of this, papers for first and other projects. We do expect to continue involvement, as you know, some interest have recurred. So again, I should do applications next year. And I already just mentioned that two of the others were not in presentations today, but will be so other events, inclusion and one, for us, and, Ireland, the projects is here, and we'll make full presentation in another venue. I want to thank, Dr. John and John, for organizing activities, and for those who helped also for the lunches. We do have one last, task for the year, someone mentioned they were notified. We still ask you to provide feedback on how the internship was and how we can improve it in future years. As we already shared, there was a vision that we carried forward, they had available to use for the work for other tournaments, including by charter. So it's, you carry the flag of data sharing forward. Think of this as something to have started on this. So my last request before lunch, because we are in this, is because we didn't have everyone in the group photo this morning. But why don't we have one now, and I has volunteers to second to that. So let's do the complete photo now. We all sign, and then lunch is, 1:40, one is so again, thanks for a wonderful summer internship.